Chapter 19, Circuit Elements. I am working through chapter summaries for Matter and Interactions. Chabay and Sherwood, great book, you should read it. But this is just a summary, going over the key points. We're in Chapter 19, Electric Circuits. And I want to just jump back for a second and talk about two big ideas from the previous chapter. First was this, delta V loop is 0. So if we have a circuit and we look at the changes of potential around a loop, we get 0. This is very important. And then also don't forget that in general, delta V is negative the integral of E dot dl. But the most important thing is it depends on the electric field and the path length. And so we create an electric field inside of a wire to make an electric current. And that leads us to this, the current. We can write the current as Q N U A E. So this is the electric current. It depends on the electric field. The greater electric field, the greater the current. And these values are also important too. This is the charge of the charge carrier. This is the number of charge carriers per unit volume. This is what's called the electron mobility. And this is the cross-sectional area of the wire. Okay, so we're going to, and then with that we have one more rule. I in equals I out. This says if I have current coming into some point, it has to be the current coming out of that point in the steady state solution. Otherwise, charge will not be conserved. So these are your loop rule and your junction rule. Conservation of energy, electric field's conservative, conservation of charge right there. Okay, let's go ahead and look at what happens if I have a capacitor hooked up to a resistor. And I'm going to start off with the simplest case of a capacitor like this. And I'm not going to draw thickness in the wires. I'm just going to draw the resistor like that. Now imagine that I have positive charge and negative charge right there, so it's a charged capacitor. Well, this charge is going to create a fringe electric field, so you will get an electric field right there, and that electric field is going to make there be a current I, but that charge will then end up on this side and it will decrease the charge. So this idea of a charged capacitor running through a resistor, you do not have a constant current. Now let's think about the other case. What about this? And I'm going to draw these as battery. This is a resistor, it's just a wire. A battery like this, and then I have that connected to a capacitor and then a resistor. And I'm going to show you these two situations. So this is some voltage EMF. That's a capacitor. If I have a battery, it's like a capacitor with the constant charge plates, but this is going to make a charge flow over here, and I'm going to get positive charges over there, which are going to push negative charges over here. Oh, I got one extra. And then so we'll get a current. But if this is 1.5 volts, this will keep on increasing in charge until this is 1.5 volt change in potential, and then the change in potential across those two is 0, so there's no change in potential for the rest. There's no electric field on here and it stops. So this will slowly increase or decrease the current through the battery. Okay, let's just play around with this real quick. I have here some batteries. I'm not sure how this will work because it's a little small. I have a battery and a wires. I can connect this to a light bulb. This is just your plain battery and bulbs, and I'll just hold that right there, and there the light's on. Now let's put a capacitor in there. So I'm going to connect this to a capacitor right there. There's my capacitor. And then I'm going to have another wire. And we can see watch what happens to the brightness of the bulb as a function of time once I connect it. Starts off bright, but then as this gets charged, then this produces a voltage in the opposite direction of that. And so you get a lower electric field and a lower current. And the current dies down, and we can see that with the dimming of the bulb. Okay, that's good. Now let's do the case right here. What if I take the battery away? Now my capacitor has charge on it, and I can connect the capacitor to the light bulb. And let's see what happens. So now it starts off bright, not super bright because it didn't have a charge all the way, and it dims down. Okay, so that's what we have. And I'm going to solve this problem for you in a short bit. But let's think about capacitors for a second. So we already had this parallel plate capacitor. If I have a charge plus Q over here and minus Q over here. I have one extra charge. Sorry about that. Then we said that the electric field inside of there, E, is constant, and it's Q over A over epsilon naught. We derived that before. That's the electric field inside of a capacitor. Now suppose that I have this separated by a distance S. I can find the change in potential. Going from here to there, let's just talk about the magnitude. So if the electric field's constant, delta V is E times S. So if I put this in for E, I get Q over A times S, all that over epsilon naught. Okay, so that's the change of potential. Now let's define capacitance. C is equal to Q over delta V. So if I do Q, and we can write this as QS over epsilon naught A. So if I take the charge and divide by Q, or delta V, I get Q over this, QS, and then I get epsilon naught A, and the Q's cancel. So this is the capacitance for a parallel plate capacitor. Epsilon naught A over S. What is capacitance? Capacitance, it tells you the ratio of charge to change in potential for a device. And this is only for a parallel plate capacitor. But it is indeed the capacitance. It tells us the ratio of charge to potential. If I add more charge, I get a greater potential. And it doesn't depend on the actual charge. Okay. Cool. Next, let's look at resistors. And I kind of already hinted at this before. But imagine that I have a wire. And it has a length L. There's an electric field inside of there. And I can measure a change in potential over the ends like that. Well, I know that the magnitude of that change in potential is E times L, right? Because if that's a constant electric field, depends on the length right there. I also know that the electric current depends on the electric field. Remember, I equals Q in A U E. Charge density, charge carrier density, cross-sectional area A, let's call it area A, electron mobility, which depends on the material, and E. So if I solve this for E, I get E equals I over Q in A U, no E. Now if I plug that in up here, I get delta V equals E, which is this, I. I'm going to put I right there. And then I'm going to put, I have an L. I'm going to put this as 1 over Q in U times L over A. And so what I did here is to say the change of potential across the wire depends on the current. This stuff depends on the material, right? And this stuff depends on the shape. And we can write this as the material properties as, I think this is 1 over sigma is 1 over Q in U. And sigma is the conductivity. We also can write this as rho. That's not sigma. Rho is 1 over sigma, and that's the resistivity. You see this both ways. But these are properties that depend on the material only. These two properties depend on the length and the area. So a wider wire would have produce more current. A longer wire would produce less current for the same voltage. But we call this whole property right here the resistance. So you can write the resistance R as equal to 1 over sigma L over A, or rho L over A. So it's one way to describe the relationship between the change in potential and the current using this property called resistance, and we measure this in units of ohms. And then that's the conductivity, or you could write this in terms of resistivity. And that's resistance. So now we have this, delta V equals IR, and that's what people often call Ohm's law. Okay, it's a relationship between the electric current flowing through a wire, the resistance of the wire, and the change of potential across that wire. It's kind of important. I think they also define current density. Let's see, did I have current density? Okay, well, let's not worry about current density. We'll get to current, oh, there it is. Okay, so we can also define current density, J, as I over A, or which is going to be sigma E, right? So that's the conductivity, and that's the electric field, and that's the current in amps, current per square meter. And this does show up later, and we're going to use this later, especially when we get to Maxwell's equations, it comes up. But it's the current density. Okay, it's in the same direction as the current. Let's look at two things, which I'm not going to derive. But now that we have circuit elements like a resistor, let's call this battery EMF, has a voltage EMF. This is resistance R. Then using the loop rule, I can say EMF equals, there's going to be a current right there. Minus IR equals 0. That's the loop rule. So if you're going in the same direction as the current, then you're going in the same direction as the electric field. So if I go, the voltage from here to there is going to be negative. So it's negative IR. If you're going across the resistor in the same direction as the current, you have a negative drop. But if I'm going from negative to positive here, I get a positive drop. So that's the loop rule right there. It's kind of simple. But what if I have more than one resistor? What if I had two resistors like this? And I'm going to derive this in another video because I don't want to spend too much time. So we'll call that R1 and R2. In this case, one of the things that's important is that the current going through R1 and the current going through R2 are the same. We can actually replace this with one single resistor called R equivalent, and that's equal to R1 plus R2. We call this series. Resistors in series. So if you have two resistors in series, they have the same current going through them, you can replace them with one resistor that's just the sum of the two individual resistors. The next one that we have is called parallel. Imagine that I have this situation. So here's R1 and here's R2. It does have a current going through, but in this case, they do not have the same current because the current's going to come into here in this junction. Some's going to go through R1, some's going to go through R2, and so they're not the same. But we can replace this with one single resistor, R equivalent, where 1 over R equivalent is equal to 1 over R1 plus 1 over R2. And I'll derive these in another video. And it turns out that for the series, this is parallel. So in series, they have the same current. In parallel, because of the loop rule, if I go around this loop right here, they have to have the same change of potential because the change of potential around the loop is 0. So one of them has to be opposite the other, so the total has to be the same for those two. So over here, if I have more than one resistor, it doesn't matter. As long as they all have the same current and they're in a line, R equivalent is just going to be, I can just keep adding them. And the same thing over here, I can just keep adding them as 1 over plus 1 over. So be careful right here, right? This is not 1 over that is the equivalent. You have to take them as fractions and then take the inverse to find the equivalent. Okay, so that's resistors in parallel and series. Let's look at a battery. And then I'll do the RC circuit. A real battery looks like this. We can model a real battery as having two ends, a ideal battery with internal resistance R int. And this is EMF. So imagine a battery like this. It's 1.5 volts. If I hook up a 0.1 ohm resistor to it, we could get 15 amps out of there, right, using Ohm's law. But there's no way this is going to give me 15 amps. It just doesn't happen. And that's because it has internal resistance. So if as the current flows through this, our voltage across it is going to drop because of that internal resistance. So bigger batteries have a smaller internal resistance and can produce a higher current. Smaller batteries have a larger internal resistance, so you can't get as big of a current out of them. But in general, the voltage across the battery, delta V battery, is going to be this internal resistance, EMF, minus R internal times the current coming out of it. So as you increase the current, that decreases. And so you can't get an infinite amount of current. Imagine hooking up a 0 ohm resistor. That says you'd get infinite current. You don't get that. And this is why you can't take a bunch of D-cell batteries and connect them in series to get and jumpstart your car. That you kind of can. There's a trick you can do. But in general, no, you can't, because they don't produce enough current. Your car battery needs, 50 amps or something like that to start that starter motor. And this just can't do it. Okay, let's do the RC circuit because it's fun. I'm going to do only the analytical version. How do we plot the electric field as a function, or the current as a function of time for an RC circuit? So imagine that I start with a charged capacitor, and I connect that. There's a switch. I connect that to a resistor R. So this is a capacitor C with an initial charge Q0. I can use the loop rule here. So the loop rule says that there's going to be a current I coming out of here and going through there. So the loop rule says delta V capacitor minus IR equals 0. But the change in potential across the capacitor is going to be equal to Q over C minus IR equals 0. Right, so as the charge decreases on the capacitor, the voltage across it decreases, and it should decrease the current. Now, I can also write I as dq dt. It's the rate of change of the flow of charge. And I can put that in up here. Now, I do have a problem. This is the charge on the capacitor. This is the rate of flow of charge. But if I put that in here compared to that, I'm going to have to add a negative sign because I'm decreasing the charge on the capacitor. So let's put this let's replace I with negative dq dt. So I get Q over C plus dq dt R equals 0. So this is a differential equation, right? Because I have a variable Q that changes with time, and then I have this thing also. Let's solve this for Q. So I'm going to subtract this from both sides. I get Q over C equals negative dq dt R. And then I'm going to multiply both sides by C, and I get Q equals negative, I'll put this as RC dq, I'll put it over that like dt. Is that right? Right. Yep. Okay. So now I'm going to divide both sides by dq, and I get this. Q over d. No, I'm gonna divide. I did this backwards. I'm gonna solve for dq. So let's divide both sides by q, and then multiply both and divide both sides by this. I get dq over q equals negative 1 over RC dt. Now I only have q on this side. I only have t's on this side, so I can integrate this from q0 to q, and I'm going to call these q primes, just so I don't get my integration variable and my final variable mixed up. And then I'm going to integrate this from t equals 0 to t equals whatever, to just t, and now I'll call that t prime. Okay, so we can integrate this. The integral of dq over q is the same as the integral of dx over x, which is the natural log of x or natural log of q. So I'm going to get the natural log of q over q0. Right? And it's really natural log of q minus natural log of q0, but we never want to write it that way because you can't, the units don't work, so we always write it as a fraction. And then over here, I'd get negative 1 over RC times T minus 1 over RC times 0, which is that. So that's my differential equation. Now I can take raise each side to the e power and get rid of the natural log. So this gives me Q over Q0 equals e to the negative T over RC. And multiply both sides by Q0. Q equals Q0 e to the negative T over RC. And that is the value, the expression for the charge on the capacitor as a function of time. Now, if I want voltage as a function of time, I can say, well, I remember up here that the voltage is Q over C. So if I divide this by C, I get V as a function of time is V0 e to the negative T over RC. And if you want to get the current, you can get the current too by taking the derivative, but that's fine. So that's one way we can do something like this to get an analytical expression for an RC circuit. If you want to add a battery in there, it's a little bit more complicated to solve. It's not impossible, but I really care about this situation right here. Okay, let's see. Is there anything else I need to talk about in this chapter? I think I am good. I'm going to make another video deriving resistors in series and parallel, but that's it for now. Read the book. Book's great. I'll talk to you later. The end. Bye.